The Auto-Spikformer is a novel approach to architecture search for spiking neural networks, SNNs, aiming to optimize the spikformer architecture while balancing energy consumption and accuracy. This method leverages evolutionary SNN neurons, ESNN, for optimizing SNN parameters and weight entanglement supernet training for vision transformer (VIT) parameters. A fitness function, FAEB, is proposed to jointly consider both energy consumption and accuracy, seeking a Pareto optimal combination. Experimental results demonstrate the effectiveness of Auto-Spikformer, outperforming state-of-the-art methods while significantly reducing energy consumption. The task of designing hybrid models that combine vision transformers, VIT, and spiking neural networks, SNN, remains challenging. The Transformer Architecture Search, TUSH, method has gained attention as an automated way to search for multiple configurations of VIT architectures. However, directly applying TUSH may not be the most optimal solution for SNN due to its neglect of the SNN search space and energy consumption. To address this gap, the authors analyze the two components of Spikformer, the transformer architecture and SNN neurons. They propose a method to investigate the optimization of both the internal parameters of individual neurons and the interconnections between neurons. The internal parameters of SNN neurons, such as threshold, decay, and time step, can be regarded as traits that can be optimized through simulated evolution, inspired by Darwin's theory of natural selection. The authors also highlight the importance of energy consumption in the optimization process, which is influenced by several factors, including input image size, embedding dimension, and firing rate. To achieve a balanced trade-off between energy consumption and accuracy, they incorporate energy as part of the fitness function and propose a joint fitness function FAEB that takes into account both objectives. The contributions of this study include the first use of neural architecture search, NAS, for spiking-based VIT, namely Auto-Spikformer, which integrates evolutionary SNN neurons and weight entanglement supernet training method to enhance efficiency and accuracy. Auto-Spikformer also optimizes the Spikformer search space by considering both energy consumption and accuracy simultaneously, achieving state-of-the-art results on the CIFAR dataset. The Vision Transformer, a pioneering model in computer vision, processes visual information by partitioning it into patches and employing a transformer encoder. This encoder consists of a patch-splitting module, multiple transformer encoder blocks, and a linear prediction head. Each block contains a self-attention layer and a multi-perception layer, with self-attention being crucial for capturing global dependencies and interest representation. Research has led to various improvements to the vision transformer, including modifications to the transformer architecture, advanced self-attention mechanisms, and pre-training techniques. Meanwhile, Neural Architecture Search (NAS) aims to automate the design of high-performance network architectures for specific tasks, achieving competitive performance in image classification, object detection, and semantic segmentation. However, searching over a discrete set of candidate architectures can result in high computational costs. Differentiable architecture search methods, such as DARTs, have been proposed to address this, enabling learning architecture coefficients using gradient descent. In parallel, spiking neural networks, SNNs, have emerged as a type of neural network that leverages discrete spike sequences for information processing and transmission. SNNs can be obtained through ANN to SNN conversion or direct training using backpropagation through time. The authors propose the Auto-Spikformer, which adopts the iterative leaky integrate and fire neuron model. This model is described by the equation UT, n equals 1 1, tau, UT 1, n, 1 YT1, n, plus it, n, where UT, n is the membrane potential, YT, n is the spike output, it, n is the synaptic input, and tau is the membrane time constant. The neuron fires a spike when the membrane potential exceeds a threshold, fifth. In this work, the authors set tau equals 2 and fifth equals 0.5. In spiking neural networks, SNNs, individual neurons can undergo an evolutionary process to adapt to their surroundings, a concept known as evolutionary SNN neurons. This process optimizes internal parameters such as threshold, decay, and time step within individual neurons, which significantly impact SNN performance. The evolutionary process begins with a population of randomly generated parameter sets, each evaluated for fitness. The fittest candidates are selected as parents for the next generation, producing offspring through mutation and crossover operators. This process is visualized in Figure 1, illustrating spike transmission, and Figure 2, demonstrating parameter modifications through mutation and crossover. The optimization of internal parameters is crucial, as it enables SNNs to adapt to changing environments and improve their performance. This concept draws parallels with Darwin's theory of evolution, where organisms adapt to their environment through natural selection. By applying evolutionary principles to SNN neurons, researchers can enhance the network's ability to process and transmit information. The evolutionary process refines the internal parameters, allowing neurons to better respond to stimuli and improve overall SNN performance. This concept has significant implications for the development of more efficient and adaptive artificial neural networks. The Auto-Spikformer algorithm utilizes a simulated evolution process to adjust the threshold, decay, and time step parameters of individual neurons in a spiking neural network, SNN, for enhanced performance. This is achieved through an optimization technique that balances accuracy and energy consumption. The search space, denoted as SS, comprises three variable factors: threshold UTH, decay tau, and time step t, as outlined in Table 1b, and visually depicted in Figure 1. The process begins with the generation of an initial set of candidate parameter sets using a random search. A new fitness function FAEB is proposed, which takes into account both accuracy and energy consumption metrics. The energy consumption is estimated by computing the synaptic operations, SOPs, which is calculated as the product of the firing rate of the input spike train, time step, and floating point operations, flops. The theoretical energy consumption of Auto-Spikformer is then calculated according to the number of multiply and accumulate, MAC, operations and spike-based accumulate, AC, operations. The energy consumption of Auto-Spikformer is determined by multiple factors, including input image size, embedding dimension, number of blocks, firing rate FR, and time step T. To facilitate comparison, these factors are normalized using a min-max scalar and assigned different weights. The accuracy and energy balanced fitness function FAEB is described as a weighted sum of the normalized energy consumption and top 1 accuracy, with alpha set to 0.5. In the context of spiking neural networks, SNNs, for image classification, a critical trade-off exists between energy consumption and accuracy. To navigate this Pareto frontier, researchers employed FAEB as the fitness function to evaluate candidate models in the CIFAR100 dataset. Figure 2 illustrates the optimal trade-off, where models like Spikformer 4384, generated using Auto-Spikformer, demonstrate superior performance. Table 2 presents a subset of these candidates, showcasing the energy accuracy spectrum. Notably, certain models outperform others in terms of energy consumption and accuracy, highlighting the importance of careful model selection. The implementation of Auto-Spikformer involves a supernet training stage and an evolutionary search stage, leveraging PyTorch 1.8 and NVIDIA Tesla V100 GPUs. Experiments were conducted on the CIFAR dataset, focusing on modifications within the SNN search space. A key aspect of this research is the comparison of FAEB with a random search approach, providing valuable insights into the efficacy of each method. By exploring the Pareto frontier and evaluating the performance of various models, this study contributes to the development of energy-efficient SNNs for image classification tasks. The authors present the results of their evolutionary search for optimal spiking neural network, SNN, architectures within the search space SS, utilizing the fitness-aware energy-based, FAEB, function as the fitness function. By plotting the energy consumption and accuracy of 300 candidates, they identify the Pareto frontier. The candidates are divided into two groups: those in the search space STs and those in STL. In Table 3, the authors showcase a subset of candidates in STs, with bold font indicating superior energy consumption and accuracy compared to Spikformer 4384. The table details the architecture parameters, energy consumption, and accuracy for each candidate. It is observed that the energy consumption is primarily determined by the firing rate, which is influenced by the time step, threshold, and decay parameter tau. The authors note that the fitness function and search algorithm favor a time step of 4, which is the maximum value in SS. They also investigate why different levels of energy consumption can result in similar accuracy and find that the network weights of these candidates are identical, despite a 25% difference in energy consumption. Further analysis reveals the relationship between the threshold value, firing rate, and decay parameter tau, observing that the evolutionary search tends to adjust the tau parameter rather than the threshold to control the firing rate. They conclude that the decay parameter has a profound effect on the firing rate in SNNs. Overall, the results demonstrate the effectiveness of the proposed ESNN method in searching for optimal SNN architectures that balance energy consumption and accuracy. The performance comparison of Auto-Spikformer with existing methods on CIFAR 10-100s is a significant aspect of the research. It focuses on the architectures STs 1, 2 and STL 1, 2, 3, highlighting Auto-Spikformer as the first transformer model designed through automated methods. This model demonstrates enhanced performance in both tasks, showcasing its potential in the field. A detailed table presents various models' parameters, energy consumption, and accuracy, including Auto-Spikformer's variance. This table clearly illustrates the Auto-Spikformer's superiority in energy efficiency and accuracy, making it a promising solution for future applications. The effectiveness of the FAEB, fitness-aware evolutionary bottleneck, is also discussed in the study. It presents a trade-off between energy and accuracy through evolutionary search and random sampling. The Pareto front of the FAEB dominates the random sample approach, demonstrating the efficiency of this method in optimizing transformer models. In summary, the Auto-Spikformer outperforms existing methods in terms of energy efficiency and accuracy, making it a groundbreaking model in the field of transformer models. The FAEB further enhances its performance by providing an optimal balance between energy consumption and accuracy, opening up new avenues for future research and development. The authors of the research paper conclude their work on proposing a one-shot architecture search method for spiking-based vision transformers, called Auto-Spikformer. This method optimizes both energy consumption and accuracy by incorporating key parameters of spiking neural networks, SNNs, and transformers into the search space. Two novel methods are proposed: Evolutionary SNN neurons, ESNN, which optimizes SNN parameters, and accuracy and energy balanced fitness function, FAEB, which balances energy consumption and accuracy objectives. The experiments demonstrate that the proposed algorithm can improve the performance of Spikformer and discover many promising architectures. The results show that the Auto-Spikformer method is comparable to the AN version, with a significant improvement in accuracy and even less energy consumption. The authors plan to conduct experiments on larger benchmark datasets or neuromorphic datasets as future work. In the realm of neural architecture search, DARTS is a notable technique proposed by Shangshang Chu et al., which robustly steps out of performance collapse without indicators. This innovative approach has been pivotal in advancing the field. Shikuang Deng et al.'s work on temporal efficient training of spiking neural networks via gradient reweighting has also garnered significant attention. Their method provides an efficient means to train SNNs, overcoming traditional challenges in this area. The importance of transformers for image recognition at scale was demonstrated by Dosevitsky et al., highlighting their potential in enhancing model performance. He et al.'s concept of masked autoencoders as scalable vision learners further emphasizes the power of transformers in deep learning. Moreover, the paper touches upon the energy problem in computing, as discussed by Horowitz, and potential solutions to this pressing issue. It is crucial to address this challenge to ensure sustainable computing practices. In the context of spiking neural networks, several key contributions are discussed. Yangfan Hu et al.'s development of spiking deep residual networks and Yifan Hu et al.'s advancement of residual learning towards powerful deep spiking neural networks have significantly expanded our understanding of SNNs. Huntsberger and Eliasmith's use of spiking deep networks with leaf neurons has provided new insights into the capabilities of SNNs, while Jordan et al.'s research on the evolution of interpretable plasticity for spiking networks has opened up avenues for future exploration. The paper concludes with a comprehensive list of significant findings and future directions, underscoring the vast potential of these techniques in revolutionizing the field of deep learning and neural architecture search. Efficient and robust spiking neural networks, SNNs, have been developed through various studies and techniques, with applications in different domains. The advancement of SNNs is attributed to works such as Katharopoulos et al.'s introduction of fast autoregressive transformers with linear attention, which demonstrated the potential of transformers as RNNs. Neural architecture search for SNNs, as proposed by Kim et al., utilized genetic algorithms to find optimal SNN architectures. To reduce energy consumption in deep SNNs, limiting spiking activity is crucial. Kundu et al.'s spike thrift method achieves this through attention-guided compression. Na et al.'s Auto-SNN combines evolutionary algorithms and gradient-based optimization techniques to create energy-efficient SNNs. Surrogate gradient learning in SNNs, introduced by Yanqi et al., enables the application of gradient-based optimization methods to SNNs. Neural architecture search is further explored through Nekrasov et al.'s approach, which utilizes auxiliary cells for fast neural architecture search and compact semantic segmentation models. Additionally, Liu et al.'s DARTS algorithm is a popular method for neural architecture search, and Liu et al.'s Auto-DeepLab applies hierarchical neural architecture search to semantic image segmentation tasks. These studies have collectively contributed to the development of efficient and robust SNNs, showcasing their potential in various applications. Deep spiking neural networks, vision transformers, and neural architecture search are at the forefront of research in artificial intelligence. Priyadarshini Panda et al. Proposed an efficient and scalable deep spiking neural network with backward residual connections, stochastic softmax, and hybridization, offering a new approach to neural network design. 44. Hu Pham et al.'s work on efficient neural architecture search via parameters sharing has also contributed significantly to the field. 45. The attention mechanism, as introduced by Ashish Vaswani et al., has revolutionized how neural networks process sequential data. 57. However, Chen et al. Challenged this paradigm with their rethinking of softmax in attention, suggesting alternative methods for computing attention weights. 46. Vision transformers, such as those developed by Hugo Touvron et al., have shown promising results in image recognition tasks when trained using data-efficient methods and distillation through attention. 56. Neural architecture search continues to play a crucial role in optimizing model performance, as demonstrated by Ning Wang et al.'s NASFCOS for fast neural architecture search and object detection. 58. Finally, Wenhai Wang et al.'s pyramid vision transformer provides a versatile backbone for dense prediction tasks without relying on convolutional layers. 59. This overview highlights the diverse range of techniques and models being explored in deep learning research, each contributing to the advancement of the field. It seems that the provided content is incomplete. Please provide the complete transcript, and I'll be happy to refine it according to the guidelines. In the realm of neural networks and object detection, several key contributions have been made. Zhaokun Zhou et al.'s work on Spikformer is a notable example, combining spiking neural networks with transformer models to achieve state-of-the-art performance in various tasks. 76. This fusion of two different paradigms holds potential for revolutionizing our understanding and utilization of neural networks. Another significant advancement is Shizhou Zhu et al.'s deformable DETR, an end-to-end object detection model that leverages deformable transformers to improve accuracy and efficiency. 77. This model's ability to adapt to complex object shapes and positions makes it a significant advancement in the field of computer vision. The paper also highlights the importance of understanding the limitations and future directions in these fields. For instance, the development of more efficient algorithms and architectures that can handle large datasets and complex tasks is crucial. Furthermore, addressing the challenges posed by real-world scenarios, such as varying lighting conditions and occlusions, remains an open problem. In addition, the integration of these models with other technologies, such as robotics and autonomous vehicles, could lead to breakthroughs in various applications. The paper emphasizes the need for continued research and collaboration among experts from different fields to fully realize the potential of these innovations. Overall, this page provides a comprehensive overview of recent advancements in neural networks and object detection, emphasizing their potential impact on future research and applications.